Hello, and once again, welcome to the second group of the s-block. We had already completed the first group, the alkali metals, with 2 lectures. And today is the first lecture on alkaline earth metals. Group 2 and erstwhile IIA, that is the old naming, 2A in Roman A. Now, needless to tell you that these groups belonging to s-block has 2 groups. The second group is beryllium, magnesium, calcium, strontium, barium, and radium. And these are less reactive than alkali metals, but more reactive than other metals, because they have lower ionization enthalpy compared to others, but higher than the respective alkali metal. That is why they're more reactive than other metals, but less reactive than alkali metals. They are not as dense or as heavy as the other transition metals. They are light metals, but not lighter than alkali metals. They are little heavier than alkali metals, little denser than alkali metals. The melting point, boiling points are relatively much greater than the alkali metals because their metallic bond is stronger. Each atom loses 2 electrons to the C, the electron C, and moreover the size of the M2 plus ion is less than M plus, so the metallic bond is stronger. Are you able to hear me? Please raise your hands to make me feel confident to carry on with the discussion on alkaline earth metals. Okay, hands down please. Now, this is a very intense level discussion that we are going to make, not a very superfluous information, simply information based discussion. It's not like that. That is why the rudimentary aspects will not be repeated here, as we had done most of these things, periodic properties, in our periodic classification program. But I will remind you from time to time. Now, radium is radioactive, and that is a source of the radiations, the radioactive radiations used initially for the treatment of cancer, radiotherapy. And electronic configuration, all of them have 2 electrons in their valence shell. They are all silvery white, except beryllium is intrinsically little grayish, and magnesium grayish white. And all of them are silvery white, but they tarnish easily when exposed to the atmosphere due to oxide layer formation. But when freshly cut, they are very, very dazzling silvery white. I will show you. These are harder than alkali metals, but softer than other metals. And the hardness, as expected, goes on decreasing down the group. As the metallic bond becomes weaker, the size increases. So the softness also increases, the hardness decreases. And beryllium is the hardest among them, so much so that it can scratch even a glass. And it has some brittleness. And needless to say, atomic and ionic radii, cationic radii go on increasing down the group, and they are lesser than the respective alkali metals. Needless to say, density, they are heavier. They are heavier than alkali metals, but the trend among them is not systematic. As you found a very good trend, excepting potassium being lighter than sodium, you remembered very well, but here the density is very weird. The density trend is absolutely irregular. I can show you the density trend. Now see, this is beryllium. It's little grayish, and it has been further blackened because of wear and tear. I mean, with the oxide formation, prolonged exposure to atmosphere. This is beryllium. Intrinsically little grayish. And this is magnesium, which is little whiter, but little slightly gray, but it's whiter. It is available in the form of ribbon. Okay. Now, calcium is, when freshly cut, it is silvery white, like sodium metal. And strontium is again silvery white, but it has been tarnished. Some of the upper part, some part remaining extremely dazzling white, I mean silvery white, but some other part, the surface has been coated and it has been tarnished. This is strontium, and this is barium. All are silvery white. And radium, this is a tarnished radium, which is very, very dangerous. If you don't protect it, then it will definitely cause pollution to the atmosphere, emitting alpha, gamma radiations, right? And a host of the daughters, as you'll be knowing in your radio chemistry, in nuclear physics, will be a source of so many other host of daughters, granddaughters, alpha, beta, gamma, and so on. That is the ionization enthalpy, as you know, are greater than the respective alkali metal and also greater than the respective group 13 member up to calcium, because they're sitting on harms. If you remember, I remind you that these three, they sit on humps because of their extra stability due to NS2 configuration. That stability factor is not found down the group, but up to these three elements, they are not only greater ionization, first ionization enthalpy than lithium, but also greater than boron. So also magnesium, not only greater than sodium, but also greater than aluminum. So also calcium, greater than potassium, also greater than gallium. These things you know. And interestingly, IE2 of these alkaline earth metals, they are less than the respective alkali metal. You know why? If I ask you a question, if you are very focused, you can tell that after plucking out a solitary electron from alkali metal, you are now left with a stable octet or duplet. And to pluck an electron from the stable octet or duplet is a hell of a job. That is why IE2 of alkali metals are much greater than the IE2 of alkaline earth metals, because the second electron is once again removed from the same valence shell. Of course, down the group, the IE1 goes on decreasing, goes without saying. As the size increases, IE1 also decreases. As size increases, IE1 also decreases. Size increases, IE1 decreases. Electronegativity and metallic character increases. Melting point, boiling point, they are greater than the alkali metals in general. But among them, there is no regular trend like density. I will show you the table, how they are significantly greater boiling, greater melting than the alkali metals. I'll show you, because their metallic bond strength is much higher. Thermal and electrical conductivity is very high, but it is greater than alkali metals. Although, this is the irony, although the density is greater, melting point, boiling point is greater due to the stronger metallic bond, but that doesn't make it a poor conductor, I mean, relatively a poorer conductor of heat and electricity. They are better electrically and thermally conducting than alkali metals because they send 2 electrons to the valence electron, I mean to the valence band, as you shall call it in your electronics, valence band, which will be easily promoted to the conduction band. So they are more electrically conductive and thermally conductive than alkali metals, despite having greater metallic bond strength. Now, oxidation state is always +2. No variable oxidation state, +2. Except beryllium and magnesium, which have appreciable covalent character, all other elements they form ionic compounds, but with some covalent character because their size is less than the alkali metals. They have some 10, 20, 15% of covalent character, but magnesium high, and beryllium compounds are really covalent, more than 50% covalent, excepting beryllium fluoride, which is ionic. Other beryllium compounds are covalent. Due to, how do you explain in your examination? Due to high ionization enthalpies. And most importantly, because B2+ ion is very small in size, high charge, so high polarizing power, and according to Paget's rule, it will have more covalent character. So much so that it is more than 50%. Magnesium compounds have appreciable covalent character due to small size of magnesium 2+, but less than beryllium compounds. If you compare between magnesium chloride and sodium chloride, you will find magnesium chloride has a lower melting point than sodium chloride. Can you believe it? If you say it is Mg2+, the lattice energy is more, then you will say, you will infer, you will conclude that this has a greater melting point. But actually it has a lower melting point because it has some appreciable covalent character, which makes the melting point less. Now it has been calculated that in sodium chloride, 29% is the covalent character, while in MgCl2, 42%. It is almost nearing the half mark. That is the reason why its melting point is less. More the covalent character, less the melting point, boiling point. More the ionic character, more is the melting point, boiling point. Now, coming to this table, you see the density data. That is the density, yes. You know, their densities were very, very less. Even lithium, sodium, you know, they're lighter than even water. Potassium is potassium also. Potassium is even lighter than sodium. Now these are, you know, this is barium is about 6 gram per cc, and this is 2.63. They are relatively denser. And melting point, you see, beryllium is 1560 Kelvin. Doesn't matter. It is in Kelvin, much greater than the alkali metals. But there is no trend. It suddenly decreases in magnesium and then increases, and it then decreases, then remains more or less constant, then decreases. So no, you know, convincing explanation can be given for this anomaly. Any attempt to do that will be simply thought to be a mere bluffing exercise. And we should all refrain from such activity rather than saying the cause is not clearly known, why there is an anomalous trend in the melting point volume as well as the density. Now see, it decreases up to calcium and thereafter increases. You can say the heaviness increases, but what happens when heaviness doesn't increase in these, so that it decreases? So let us forget about that. Now coming to, you know, these are so reactive, they also are not found in elemental or native state. They are always available in nature in combined state, as their chlorides, their sulfates, their carbonates, and so many other minerals and ores as we shall see. When talking about hydration enthalpy and electrical conductivity in aqueous solution. Now, in this similar manner, since their sizes are less than the respective alkali metals, they have a relatively greater hydration energy than alkali metal ions. But among them, it goes on decreasing. As the size goes on increasing, the charge density goes on decreasing, Q by V, then hydration enthalpy also goes on decreasing, right? So if that is the case, then the opposite is the trend for the electrical conductivity of these hydrated ions. The most conducting is the hydrated barium ion because its size is the least inside water, and beryllium 2+ is heavy, thick, as if it is wearing the thickest water coat. So its conductivity is the minimum. Now these have so high hydration energy that since beryllium compounds are covalent, there is no chance of forming any crystalline ionic compounds. Other elements, they form ionic hydrated crystals. All others, because they have high hydration energy, they can be crystallized with water of crystallization. Magnesium can go up to, this can be 12. Of course, we have to reduce the temperature, I'll tell you. But at room temperature, it is 6. MgCl2.6 water, calcium chloride 0.6 water. You can have 3, 4. Depending on the temperature, you can have variable number of water of crystallization. Now, coming to the next point, reducing power. That is the most important point. I remind you, in alkali metals, something went a little weird to make lithium number 1. Despite having the highest ionization enthalpy, it was the number 1 reducing agent because its standard potential was 3 point something. Forget about minus plus. More the reduction potential, numeric value, greater is its reducing strength. Lithium was the most powerful, and very, ironically, sodium was the worst, 2.71 volt. And the unusual high sublimation energy or atomization energy was responsible for making sodium the last boy in the class. And I remind you, the process of the conversion of a solid metal into hydrated ion involves 3 energy terms, out of which 2 are positive, 1 is negative. IE1, and here one more. IE1, IE2, both are positive. And of course, the beginning sublimation energy, because all of them in their standard states are solids. You have to vaporize. That is called the heat of atomization or the sublimation energy. That is positive. IE1 and IE2 are positive. And then hydration energy is negative. The sum total of these 4 energy terms is absolutely controlled by the first ionization enthalpy. So here the trend is very, very systematic, and it goes in hand with the trend in ionization enthalpy. More the ionization enthalpy, less is the reducing strength, less is the numeric value of electrode potential. Now here the trend is not anomalous like alkali metals. Beryllium is the least powerful reducing agent, having SRP 1.97. Forget about minus. Reduction potential is minus 1.97. Magnesium, calcium, strontium, barium. This is the order of, decreasing IE1. The same is the trend with the reduction potential. Because there, hydration enthalpy was, making topsy-turvy to lithium. But here, IE1, IE2, both IEs are involved. And that cannot be subsided by the high hydration and enthalpy of Be2+. Hydrogen enthalpy is only one value, but IE1 and IE2 are two values. So these two values cannot be overweighed by the high hydrogen enthalpy of B2 plus. So the controlling factor is IE1 and I2, and the trend of IE remains the same as the trend in the reducing strength. Beryllium is the worst, radium is the best. And out of them, beryllium and magnesium, they are least. Calcium, strontium, barium, radium have greater reducing strength than sodium. Sodium is 2.71, and these have greater. These have greater reducing strength than sodium. But beryllium, magnesium has lower reducing strength than sodium. And strontium, barium, radium, these three have similar reducing strengths as potassium, rubidium, cesium. They were also having similar, same, about 2.9. So these are the same, 2.9, 2.9, 2.9. So strontium, barium, radium, as well as potassium, rubidium, cesium, they have similar reducing strength. Calcium has a greater reducing strength than sodium, so also all these. And sodium, of course, is hero to these two, beryllium and magnesium. Then you have sodium, right? Now, the high numeric value of these potentials, why they are strong reducing agents, although they have high IE1 and IE2, because of the high hydration enthalpy. This high hydration enthalpy makes the net energy requirement less. That is why their reducing strengths are greater, their SRPs are negative, and hence they're good reducing agents, and they're comparable with alkali metals. That is the important point you have to remember. So 4 of them. So for radium, you forget, they are not available in the laboratory, just for sake of fun. So excepting calcium, strontium, and barium, these two are little less reducing than sodium, and these are more reducing than sodium and equally reducing as potassium, rubidium, and cesium. So they are powerful reducing agents because of high hydration enthalpy is the key. Now, beryllium has the least reducing strength, not only due to high IE1 and IE2, but also due to high heat of atomization. Sublimation energy also is very high. That makes beryllium the least reducing, and its SRP, numeric value, is the least. Now, coming to the flame coloration, beryllium and magnesium, they do not show any color in the flame, because they have high IE1 and IE2, and the flame doesn't carry that amount of energy which can excite the electron to the higher level, and its de-excitation might be responsible to produce emission spectrum. That doesn't happen in the flame. But others, they are suitable for flame photometry. So nowadays, flame photometric instruments are available, which will not only detect from their colors, but also estimate how much calcium is there in that compound. I mean, in that sample, how much strontium is there in that compound. Yes, the pronunciation of strontium is not strontium, it is strontium. The American pronunciation says it is strontium. You might be wondering, I'm saying strontium. Yes. So calcium gives a brick red color here. These things we have already done in our group 1. Calcium gives a brick red, which is transient. It vanishes quickly. Crimson, strontium gives crimson, and barium gives pea green. These are used in qualitative estimation in flame photometry. That for common purpose in the classroom, students like you detect by the flame test the presence of these metal ions in the salts. Chemical property, in all the chemical properties, The reactivity is the least for beryllium. Slowly the reactivity increases up to barium. And because the ionization enthalpy goes on decreasing, because the reducing strength also goes on increasing, so also the reactivity for every chemical with every other chemical. Let's say, for the example, with water, how does these elements react with water? Beryllium does not react with water. In many literature, you'll find it doesn't. But nowadays, beryllium has been found to react with water at a very, very high temperature, superheated steam to produce beryllium oxide and hydrogen. But all others can react with cold water. Magnesium, the reactivity is very, very less. So much so that it takes a long time to produce a distinct alkalinity in the resulting solution. Because hydrogen goes away, rendering the solution alkaline due to hydroxide ion formation. So you can see bubbles coming out. If you go for a magnifying glass, if you look to that magnesium wire or a seed, you'll find bubbles will be sticking. It will react in cold water, as opposed to in many texts written no reaction with cold water. No, I have seen. You will also see, you can Google search, you find magnesium does react with cold water, but very slowly. That is why boiling is necessary. In boiling condition, it reacts faster to produce their hydroxide and hydrogen. This magnesium hydroxide is sparingly soluble. It's not much soluble, and hydrogen escapes. But reactivity can also be improved without boiling by making amalgam with mercury. Magnesium amalgam reacts with cold water more rapidly than only magnesium. Now, if you use steam, then you get oxide. If you get water, not steam, then you get hydroxide, right? If you put magnesium oxide in water and boil, you will get hydroxide. But all the rest react very fast in cold water, not faster than the alkali metals, but yes, fast. They are as much reducing as calcium is even more reducing than sodium, and these two are similar reducing than like potassium and rubidium and cesium. But I told you the kinetics plays a big role. Their melting points are much lower than the melting points of all these. So they don't melt and spread well. So the reactivity of these, they are less than the alkali metals. Even if the reducing strengths are similar, but the reactivity is not as, explosively violent. You have seen how potassium, how rubidium, and how cesium reacts with water. But you've seen an experiment where the glass, tub that exploded and broken down into pieces. Such a thing doesn't happen. So it's not the reducing strength, not the potential, reduction potential or the electrode potential will tell you the reactivity. Reactivity is mostly a kinetically driven. But sometimes thermodynamics becomes friend to kinetics. In such case, you find it goes hand in hand. But here with water, they react with cold water rapidly, but not as rapidly or as explosively like alkali metals, despite having similar reducing strengths. Now coming to the nature of hydroxides. Beryllium hydroxide is amphoteric. It can react with acid, HCl or H2SO4 forming salt, and also with strong bases like Na or KOH to form berylate. This is the real formula of berylate, BeOH whole 4 2-. But we can sometimes abbreviate, make a cheating expression of berylate as Na2BeO2. I think examiners won't mind to see this one. But the real berylate formula is this. And slowly and steadily, we enter into more fascinating aspects of alkaline earth metals. I told you that this is not a superfluous discussion, and just telling you the rudimentary information. We will be talking about the hardcore underlying principle behind everything. For example, look to the solubility and basicity of these hydroxide, beryllium hydroxide down to barium hydroxide. The solubility goes on increasing down the group, but relatively they are less soluble than and less basic than alkali metal hydroxide, because the solubility will decide the basicity. More the solubility, more is the hydroxide ion concentration, and hence more is the basicity. Now, beryllium hydroxide is almost insoluble. Magnesium hydroxide is sparingly soluble. You can very well work out a numerical on MgOH whole 2 with the KSP data. I'll give you, solubility product. That is the guiding, the constant to know, have an idea about the solubility. Less the KSP, less is the solubility. Calcium hydroxide is partially soluble, is not much soluble. It's called moderately soluble. This is the lime water. When you take slag lime and dissolve in water, it won't dissolve much. Then you have to, filter out most of the calcium hydroxide, and the remaining solution we call lime water, which is used for passing carbon dioxide or sulfur dioxide gas. And the other two, strontium and barium hydroxides, they are fairly soluble. If I give you the data, you'll be very, very surprised that beryllium hydroxide is almost insoluble. The KSP is of the order of 10 to the power negative 22. And magnesium hydroxide is 10 to the power negative 12. So, and in terms of gram per liter, this is almost negligible, and magnesium hydroxide is 0.0064 gram per liter is soluble. And calcium hydroxide, yes, 1.7 grams per liter. It's, KSP is not so high. It is almost 10 to the minus 6, negative 6. And here, since these values are large, instead of giving their KSP values, you can find out the KSP values from this data, making it moles per liter first, and then 4x cube, x to x, x into 2x whole square, 4x cube. And first of all, you have to make it moles. This is gram per liter. 17 grams of strontium hydroxide, is soluble in 1 liter solution. Barium hydroxide is still high, 39 grams per liter. I have not calculated 4x cube and not given, usually you won't find the KSP values for soluble salts. Only sparingly soluble salts, ironically, they are given, but highly soluble salts, you may find out from their solubility data by the whether x square method or 4x cube method or 27x to the power 4 method, depending on the type of the salt or the compound. Now, interestingly, calcium hydroxide is the one which dissolves exothermically, releasing heat. I'm not talking about the chemical reaction of calcium oxide to calcium hydroxide. That is exothermic. I'm asking the dissolution of slag lime in water. That is also exothermic. That is why the solubility decreases with increase in temperature. Now, I can show you, what is Lee-Satellier's principle, calcium hydroxide plus AG, this is solid, and this is AG, giving you calcium, this becomes soluble AG plus 2 OH minus AG plus heat. And if you apply the Lee-Satellier's principle, if you increase the temperature, system will try to reduce the temperature by favoring the backward process. The solubility will decrease. So that is the case with only calcium hydroxide. Remember this. Others, they do not dissolve and exothermically, they dissolve endothermically. So solubility increases with increase in temperature, but calcium hydroxide, the middle one, the solubility decreases with increase in temperature. Now coming to the formation of oxide, how does these metals react with air or oxygen or the components of oxygen like nitrogen? Are you listening to me? To take stock of what is going on, I would like to just interact with you. Are you listening to me with all your focus and attention to make this class a memorable one? And whoever will watch this class, this record video later, will definitely enjoy and gain from the experience of this instructor for the last more than 40 years of teaching chemistry to the higher level school students. So let me moisten my throat with a bit of water. Now in air or in oxygen, magnesium is the only one which burn very, very brilliantly. Very, very brilliantly. Magnesium burns with a blinding white light. Your eyes will be completely affected. You will definitely take away your eyesight. So blindingly powerful white light. Excepting barium and radium, which form peroxides, just like sodium was forming largely peroxide, and potassium, rubidium, cesium, they were forming superoxides. Here, all the beginners, they will be forming normal oxides, and barium and radium, they will form peroxides because of the sites matching. So in general, M plus O2 MO, it's not monoorder. This is the metal oxide. Beryllium also will form beryllium, but they can also react with nitrogen, but not as easily as with oxygen. You get a minor product of nitride, but if you heat them in this only nitrogen environment, heat it, then you get nitride. But in air, the major component, major compound, major product is oxide. Nitride is the minor product, right? Now, look, this one here, I must write down magnesium burns all of them. Somewhere I must write blinding white light. I can write here. Magnesium burns with blinding white light. That is why it is used in flash bulbs, in photography, in incendiary bombs, because it gives a blinding white light. Now, just to have a feel how it burns, let us see a few seconds video how magnesium burns with a blinding white light. Such is not the case with others. They burn, but they don't give such blinding white light. Now, you will gather, if you put a paper, you will find a white granules of magnesium oxide. Then coming to the next slide, that is, you can get oxides also by heating nitrates carbonates and hydroxides. All of them on decomposition will give you their respective oxides. Nitrides can be obtained when you heat the metal in only nitrogen atmosphere, you get pure nitride. Except beryllium nitride, which is covalent, others are ionic. Now, they all react fast in dilute non-oxidizing acids like HCl, sulfuric acid, to produce hydrogen gas. And of course, we will see that they also react with other oxidizing acids, for example, conch sulfuric acid, to produce sulfur dioxide, nitric acid to give you some N2O or NO2 or NO, or sometimes hydrogen in a very, very rare possibility with oxidizing acids. We'll see that. And the nature of oxides is similar to the nature of hydroxides. They're all basic oxides and ionic. Beryllium oxide is amphoteric and has appreciable covalent character. The solubility and basicity order is similar to their hydroxides because they produce hydroxide in water. They react with water, forming their hydroxides, except beryllium oxide, which doesn't react with water. Magnesium oxide needs boiled water for dissolution. It has a very poor solubility in or reactivity in cold water. So you have to heat it so that you can get magnesium hydroxide. So I have another specific arrow mark where heating is required. I must give it here. And then Control S. Now coming to this is most vital. You just try to listen to me with utmost attention. How halides of these alkaline earth metals can be prepared and what is their general trends in their solubility and melting point, boiling point. Now, they can be all prepared by direct combination with the respective halogen. But beryllium fluoride cannot be prepared so easily. It is prepared indirectly from ammonium fluoroberylate by heating it. First, this complex, then heating, you get beryllium fluoride. Or you heat beryllium oxide with carbon and the chlorine environment at high temperature to give you beryllium chloride. This is beryllium fluoride, this is beryllium chloride. These are the specific preparation of beryllium halides. Others can be prepared directly. You can also get these halides by treating HX, hydrohalic acid, HCl, HBr, HI, HF with carbonates, their oxides, or their hydroxides. All of these react with their corresponding hydra acids of halogens to form the corresponding halides. It's not a big deal at all. Now, let us now focus on beryllium halides alone. Beryllium halides alone. Can you tell me, in case of group 1, what was the solubility pattern of lithium fluoride that we learned from the anomalous behavior of lithium? Can anybody raise your hand? About lithium fluoride, LiF, lithium phosphate, lithium hydroxide. What was the point about their solubility in water? Anybody who wants to? Yes, you can try. Raise your hand. I will ask you to unmute. Lithium fluoride, if you look to the anomalous behavior of lithium, you will find lithium fluoride, lithium phosphate, lithium hydroxide, they are sparingly soluble. But here beryllium fluoride is soluble, highly soluble. And other fluorides are sparingly soluble. Now, once you know this, then you account for why. Because it has got high hydration enthalpy, both fluoride ion and beryllium 2+. As an ion and a cation, they are very small. They produce a lot of hydration enthalpy, which is far greater than the respective, the lattice enthalpy. So solubility is high. Others, lattice enthalpy cannot be overruled by the hydration enthalpy. So other fluorides are sparingly soluble, excepting beryllium fluoride. For beryllium fluoride, hydration enthalpy is, yes, a chart is there. Yes, my voice is fluctuating sometimes. Yes, I understand that. So that is why I told you that the recording will be not fluctuating. I suppose you can play on the video and look that part. Now, am I audible? Am I audible now? Okay. Now, we were discussing only about beryllium halides. Beryllium fluoride is sparingly, highly soluble, while other fluorides, I'm talking of other, not only fluorides, other halides are sparingly soluble. No, other fluorides, other halides. I mean, beryllium chloride, bromide, iodide. I'm talking of only beryllium. Beryllium fluoride is soluble. Beryllium chloride, beryllium bromide, beryllium iodide are sparingly soluble. And they are in fact covalent and soluble rather in organic solvents like acetone, like carbon tetrachloride, chloroform. They're soluble because they are largely covalent. And the covalent character is maximum in beryllium iodide because iodide ion has a larger polarizability. Beryllium chloride is no doubt sparingly soluble, but it reacts with water. Immediately, it reacts with water. So beryllium chloride, when the bottle is opened, it produces dense white fumes. Why? Because the atmospheric moisture reacts with beryllium chloride easily and hydrolyzes to beryllium hydroxide, and HCl fumes come out. HCl comes out, it sits on the atmospheric moisture and produces a mist that is called the HCl fumes. And beryllium chloride in the pure state remains as a dimer, B2Cl4, in the liquid state and even in the vapor state, which continues to remain up to 1200 Kelvin, it remains as a dimer. At 1200 K, it dissociates into monomer, BeCl2, which is a covalent compound. All these are covalent. And this is sp hybridization of beryllium, and it is a linear molecule. That is only beyond 1200 Kelvin, it remains as BeCl2, otherwise B2Cl4. Why? Because it is a Lewis acid. And in the solid state, it remains as a polymer. A lot of BeCl2 molecules, they are connected by dative bonds, forming a long chain. Now I'm showing you the structure. This is B2Cl4 dimer. That is in the liquid state and vapor state up to 1200 K. Now this was BeCl2 linear, but now this is, this is a trigonal planar. The hybridization has been changed from sp to sp2. And here the lone pair of one chlorine donates to the vacant p orbital of the other beryllium. And so also here. So that gives B2Cl4. Beryllium has vacancy. It has a BeCl2 is a quartet, 4 electrons. It has got 2 p orbitals vacant. One p orbital is used. Other p orbital is also there to accept electrons. So this is a Lewis acid. Anyone which will accept electron is a Lewis acid. We have not yet studied Lewis concept of acid and base. We're doing at the end. And this is the polymer, BeCl2 whole N. Similar type continues. Here, this continues to form a long chain. N is very large. And this distance is 263 picometer, and this is 98 degree, and this length is, 202 picometer. It's nothing to remember all these things. Now, coming to how these halides, then we forget about beryllium. We talk in general, the halides, they form hydrates easily, except beryllium halides, which are covalent. Others, they form easily, they're hydrates. While you crystallize in water at different temperature, you will find different number of water of crystallization molecules will be associated in these crystals. If the temperature is low, then it can go up to 12. 8 ordinarily at room temperature up to 116.7, it is 6. And at this, it breaks down to 4. The 4 continues up to 181. Then it breaks down to 2. The 2 continues up to 300. Then after 300, it breaks down to 1. 300, beyond 300, it becomes 1. And if you still hit, it reacts. They chemically react to form first the basic magnesium chloride, Mg, OH, Cl, and HCl. Further, if you heat this, then again HCl will go to give you a highly infusible, high melting magnesium oxide. So that is the case when you heat magnesium, particularly magnesium. If you heat, it doesn't leave water so easily. Others will leave water, but magnesium has an affinity for water. They will chemically react. The last water will not go. It will react. Then calcium chloride 6, strontium chloride 6, and the tendency to form hydrates decreases as the size increases. The metal ion size increases, their charge density decreases, and hence their power to attract water decreases. So barium doesn't form hexahydrate, it forms only dihydrate, right? Now, coming to their melting point, boiling point. Now, the melting point, boiling point of halides increases down the group. Unlike alkali metal, for a particular halide, it goes on increasing down the group. Particularly, I'm not talking of fluorides, which are ionic compounds, but others are having appreciable covalent character, chloride, bromide, iodide. So their melting point goes on increasing. That is the opposite trend that we found for alkali metal chlorides. Of course, lithium chloride was the lowest, sodium chloride, then potassium, then rubidium, then cesium was, I think it was 600 something. And lithium chloride was the least because of some appreciable covalent character. But here is the opposite. Beryllium chloride has the highest, covalent character. Therefore, the melting point is the least. And barium chloride has the minimum covalent character or maximum ionic character. Hence, its melting point, boiling point is the maximum. So the trend of melting points of halides is the opposite of that found in alkali metals, excepting lithium compounds, which has got some anomaly because of covalent nature. Now, coming to the solubility of these halides, let us study, because in your examination, particularly in your competitive examinations, you will find some intricate questions on what I am going to discuss or I am discussing now. So coming to solubility of these halides, fluorides, I have already told you, beryllium fluoride is soluble, while other fluorides, these are sparingly soluble. You can very well solve the numerical, giving its Ksp value, 10 to the power negative something. So they are sparingly soluble. Beryllium fluoride is highly soluble. Coming to chlorides, these are also, beryllium chloride is sparingly soluble, as I have already told you, but all the other halides are sparingly soluble of beryllium. Now, but it reacts with water. That is the bad quality, that is insoluble or sparingly soluble, but immediately it reacts, forming beryllium hydroxide. The ultimate thing remains beryllium hydroxide, and HCl goes out. It fumes in moist air. Chlorides of other metals, and this is beryllium, but chlorides of other metals are soluble. Fluorides of other metals are sparingly soluble because of high lattice enthalpy. But chlorides of other metals are soluble, but the solubility goes on decreasing down the group. I will tell you why. Magnesium chloride is the most soluble and barium chloride is the least soluble. Because as size increases, what happens? The controlling factor is the lattice enthalpy. The lattice enthalpy decreases. Their hydration enthalpy doesn't change much. So the lattice enthalpy is the maximum here. And therefore, I'm sorry, their lattice enthalpy doesn't change much because they are large size anions. So lattice enthalpy is not the controlling factor. It is the hydration enthalpy which is the controlling factor. More is the hydration enthalpy, more is the solubility. So remember, for large size anions, chloride, bromide, iodide, sulfate, carbonate, chromate, dichromate, phosphates, the analogy, the logic is the lattice enthalpy factor is not the controlling factor. It goes on definitely decreasing down the group, but that is not the decrease is not drastic. It's very gradual. So that's not the controlling factor because they are large size. When you are standing beside an elephant, you take the distance between the elephant's center and your center. That distance you measure, and you replace by a thick person, a obese person, and take the measure. What the difference, when the anion is obese, elephant, like carbonate, chloride, bromide, iodide, then the metal ion changing from beryllium to calcium to magnesium to strontium to barium hardly changes the inter-ionic distance. So lattice enthalpy doesn't change much, but the hydration enthalpy of the metal ion, that significantly decreases. That controls the solubility. More the hydration enthalpy, more is the solubility, and therefore magnesium chloride is most soluble and barium chloride is least soluble. Same is the trend with bromides and iodides, similar trends to chlorides, right? So the bottom line is fluorides are insoluble, excepting beryllium chloride. Fluorides are insoluble because of high lattice enthalpy. Fluorides of all alkaline earth metals are insoluble, excepting beryllium chloride. And chlorides, excepting both beryllium chloride, which is sparingly soluble, other chlorides are soluble. Beryllium chlorides are, beryllium chloride is beryllium chloride, beryllium bromide, beryllium iodide. They are sparingly soluble, but they are hydrolyzed easily to form beryllium hydroxide and the respective hydrogen acid gas, HX gas. All other halides, chloride, bromide, iodides, they are soluble, and the solubility goes on decreasing down because chloride, bromide, iodide ions are bulky, obese anions. Now, formation of hydrides. We are left with only 10, I think 10 slides. Now, formation of hydrides, when you heat the metal with hydrogen, let me import the heat arrow mark. When you heat the metal with hydrogen, you get its corresponding hydride, which are ionic, except beryllium doesn't react directly with hydrogen. Beryllium doesn't react directly with hydrogen, but you can prepare beryllium hydride in indirect method. Like beryllium chloride can be reduced by lithium aluminum hydride to give you beryllium hydride, or beryllium chloride can be reduced by lithium hydride to give you beryllium hydride. And all these hydrides, they readily react with water to form hydrogen and the corresponding metal hydroxide, just like alkali metal hydrides. There is no point to tell you these are redox reactions where metal hydride goes from -1 to 0, hydride from -1 to +1. This is +1 to 0, I'm sorry, +1 to 0, -1 to 0. So this is a comproportionation reaction. +1 to 0, -1 to 0, right? Then coming to carbides, this is again very simple. These metals can form their carbides very easily, but beryllium forms with from their compounds, oxide and carbide. Beryllium oxide, I'm sorry. Beryllium oxide reacts with carbon to produce beryllium carbide. And these carbides, particularly beryllium carbide, is called methanide. The carbon has an oxidation state of -4, B to C. Why? Because it is when heated with water, it produces methane. So this is metathesis, non-redox. Non-redox reaction, this is -4, this is -4, and beryllium hydroxide. That is why beryllium is the only one which forms methanide with a carbon oxidation state -4. We'll know the reason why such a thing happens in our carbon family, but for now, others, they are directly combined, or also their oxides also combine to form acetylides, where carbon is -1. Why it is called acetylide? When you treat these carbides with water, you will not get methane. Instead, you get acetylene having an intrinsic triple bond, acetylide ion. So this is acetylene, this is magnesium or calcium carbide, but it is really calcium acetylide. There is an inbuilt carbon-carbon triple bond, which remains here. So it is acetylene, and you know, this is used for ripening fruits in an artificial manner. So you carbide, they sprinkle water, they sprinkle carbide powder, calcium carbide powder, then water, then acetylene gas comes out, and that is responsible for the artificial ripening of fruits. Now, this is all about carbides. Beryllium, remember, beryllium forms methanide, while others form acetylide. Coming to reaction with acids, I have already told you they displace hydrogen from the non-oxidizing acids. But from oxidizing acids like conch, sulfuric acid, it produces SO2. Nitric acid, I have given you one example. If it is moderately conch, it is NO. If it is dilute, it is N2O. If it is conch, it is NO2, reddish brown. But magnesium is the only alkaline earth metal which reacts with a very dilute nitric acid, 1% dilute. That is W by V. That gives you hydrogen gas. And its partner is manganese. That is not an alkaline earth metal. It's a transition metal. So these magnesium and manganese, they are the only two metals which react with very dilute nitric acid to form hydrogen gas. Otherwise, you will get either NO or N2O or even N2, sometimes ammonium nitrate, because ammonia cannot escape, it forms ammonium nitrate. You must have to revise. Balancing, when you write down in your copies, you don't copy these coefficients from my PPT. Instead, you take one, say magnesium. Instead of M, you take Mg and start your business. The change in oxidation number in the reducer is multiplied with the oxidizer and vice versa, and then go for the inspection, and if required, some additional spectators can be adjusted by increasing the number of reactants, so that you know. Then talking about carbonates, how they form their carbonates and what is their solubility pattern and what is their thermal stability pattern. Now, these carbonates are formed when their hydroxide solutions are allowed to react with carbon dioxide. Carbon dioxide is passed through the suspension of these hydroxides or solutions of these hydroxides. You get their corresponding carbonate. A limited quantity. If you pass larger quantity, then this will form bicarbonates or hydrogen carbonates, which are soluble. So don't do that. Limited quantity of CO2 will produce carbonate. Or if you have halides, then you have a double displacement reaction with a sodium carbonate to produce this precipitate. They are all white solids. And solubility pattern is very fantastic. As I told you, when it is an elephant, like chloride, bromide, iodide, carbonate, sulfate, then it is the hydration enthalpy, which governs, which controls the solubility. More is the lattice enthalpy, more is the solubility. So beryllium carbonate is soluble, though it is covalent, but it is soluble. Magnesium carbonate is little less soluble, but it is much more soluble than these three guys, which are sparingly soluble. You can now solve a problem on solubility product. KSP will be 10 to the power negative something, but this is 10 to the power -2 or something like that. I have not given you the data, but beryllium carbonate is fairly soluble and the solubility goes on decreasing. That is the trend with chloride, bromide, iodide, carbonate, sulfate, chromate, phosphate, and elephant-like anions. These sparingly soluble carbonates react with excess of carbon dioxide to form their bicarbonates or hydrogen carbonates. These hydrogen carbonates, unlike the alkali metal ones, they are only soluble, they are only existent in solution. You can't isolate calcium bicarbonate. Once you heat it and try to isolate, it will be forming, calcium carbonate. So only these bicarbonates are known in solution. Now, just I compare with the solubility of hydroxides. Beryllium hydroxide was least soluble, sparingly soluble. I gave you the solubility product 10 to the power -22. Magnesium hydroxide is no less, 10 to -12. Calcium hydroxide was moderately soluble, 1.7 gram per liter. And these strontium hydroxide, barium hydroxides are fairly soluble. But the opposite trend is here. Beryllium carbonate is soluble, while others are sparingly soluble, and solubility goes on decreasing down the group. And hydroxide, there's a small size anion. For small size anion like OH-, it is not the hydration enthalpy which controls the trend. It is the lattice enthalpy which controls the trend. Because you and me, a lean person like me, say X, and a lean person like Y. So when X remaining constant, say for example, hydroxide is a lean person, like X remaining constant, and the other one changing from B2+ to Ba2+. So there is a significant increase in the internuclear distance. Unlike the elephant and we varying between us, elephant remaining static. So the large size anion, something as different, is the hydration enthalpy, the controlling factor. But small size anion like OH-, it is the lattice enthalpy, is the controlling factor. The lattice enthalpy changes is reduced in a drastic way. So more the lattice energy, less is the solubility. So beryllium, being the smallest in size, has the largest lattice energy, the solubility was the least. Barium 2+ has the largest size, least lattice enthalpy, and hence maximum solubility. Right? Now we are almost inching towards the end of our program. It is already 1 hour 12 minutes, and I'm sorry, 1 hour maybe 10 minutes. Yes, we are going quite fast. Now these carbonates, they decompose in a very interesting way. Beryllium carbonate is the least stable. And in fact, if you want to stabilize beryllium carbonate, you have to protect, store in an atmosphere of carbon dioxide. It is highly unstable. And at 100 degrees Celsius, it decomposes all, forming their corresponding oxide and carbon dioxide. And the stability goes on increasing. As size increases, the matching between the metal ion and carbonate, the elephant, becomes better. The crystal lattice becomes stronger, and hence the thermal stability is becoming more and more. Beryllium is such a thin, carbonate is such a large, and it will be trying to pull out oxide ion because it has high polarizing power. That is Fajan's rule. And slight heating, it will pull out oxide ion from carbonate ion, releasing carbon dioxide free, and it forming a covalent beryllium oxide. Because of high polarizing power of Be2+, it has a tendency to pluck out oxide ion from carbonate, the bulky carbonate ion. Stability is the minimum. And we can write down, due to high polarizing power B2+ has also easily removes O2 minus ion from carbonate. That's is other way. As the size increases, the polarizing power decreases, and the tendency to pluck out oxide ion becomes less. Well, similar is the trend with sulfates. You can prepare sulfates of these metals by reacting the oxides, hydroxides, carbonates with dilute sulfuric acid. Carbonates, oxides, even the metals with dilute sulfuric acid, all of them will form their sulfates. And on crystallization, they form hydrated crystals. Magnesium form 7 water, that is naturally available in Epsom salt, as we shall study. And this is gypsum salt, is naturally available, calcium sulfate dot 2 water. Magnesium has the highest power of attracting more number of water molecules because of its smaller size. Even in chloride, it can go up to 12, as we have seen. Now, similar trend is found in the solubility of sulfates. Beryllium sulfate and magnesium sulfate are really soluble. And as we go down the group, becomes increasingly sparingly soluble, and we call insoluble. Calcium sulfate is moderately soluble, and these are really, as we can dare say, insoluble. Yes, we can solve a problem with Ksp 10 to the power negative, hugely negative. So same thing happens, large size elephant like an ion, it is the hydrogen enthalpy which controls. More the hydrogen enthalpy, more is the solubility. And thermal stability is the similar manner in the carbonate. Beryllium sulfate is least thermally stable. At the lowest temperature, it decomposes, and barium sulfate is most thermally stable. It requires much higher temperature to break down into this, the oxide, sulfur dioxide, and oxygen. Now, nitrate formation is very cool, because either you take any form of nitric acid, it will form nitrate. Whether dilute, whether moderately concentrated, whether very dilute, or very dilute, like 1%. It will form the nitrate. And all nitrates, they will on decomposition will form NO2 and O2. Unlike sodium, potassium, rubidium, cesium nitrates, which form their nitrides and oxygen, excepting lithium nitrate. These nitrates, they all form NO2 and O2 as well as MO. Same is the case with oxalate and chromate. You can get oxalate by using ammonium oxalate or oxalic acid with metal halides, and potassium chromate with metal halides, and their solubility and their thermal decomposition pattern is similar, because they are all elephant-like anions. With liquid ammonia, do you remember in our alkali metal program, we know when we treat a metal, alkali metal with liquid ammonia, it forms an intense blue solution. And that intense blue solution contains the ammoniated metal ion and ammoniated free electron. Same thing happens here. The alkaline earth metal dissolved in liquid ammonia will form ammoniated metal ion with ammoniated free electron, and that makes the solution highly conducting, much more conducting than the alkali metal, because it has 2 electrons per atom. But slowly and steadily, but more Rapidly, when you add a bit of iron or platinum or any impurity metal ion, transition metal ion, then it rapidly breaks down to form hydrogen gas with respective amide. Calcium amide, this is magnesium amide, and this is not amine. It's not organic, it is inorganic. These are called amides. Beryllium, magnesium do not react with ammonia. I am sorry, I withdraw. Magnesium amide is not formed by this way. Calcium, strontium, and barium. Beryllium and magnesium, they are tough. They don't react with liquid ammonia. Now, I have already discussed several times the general explanation on solubility of metal hydroxide with a small size anion. And the elephant-like anion like carbonate, sulfate, oxalate, phosphate, and chromate. In small size anion like OH minus, the decrease in lattice energy going down the group is more drastic. The size increases very significantly. So the controlling factor for which it controls, it means the lattice enthalpy controls. More the lattice enthalpy, less is the solubility. So beryllium hydroxide was less soluble. But for elephant-like anions, the hydration enthalpy decreases drastically, for which hydration enthalpy, it's not He, it is hydration enthalpy controls the solubility. Greater the He, greater is the solubility. Therefore, beryllium carbonate, beryllium sulfate, beryllium phosphate, beryllium chromate, beryllium chloride. Of course, beryllium chloride is sparingly soluble, but it hydrolyzes. Don't talk about that. They are soluble, and solubility goes on decreasing down the group for large size anions, right? You have already done. You just have a look. Beryllium copper alloy is for making high strength springs. Beryllium is used for making windows in X-ray tubes. Magnesium aluminum alloys, particularly magnesium, used in aircraft construction. Milk of magnesia was used as an antacid. Now, my light has gone out, but we don't bother. We will complete this program. Magnesium carbonate was used in toothpaste. Calcium is used as a reducing agent in many metallurgical processes. Calcium barium used to remove air from vacuum tubes. Radium used in radiotherapy, treatment of cancer. Magnesium ribbon powder used in flash powder, incendiary bombs and signals, and many other hosts of many applications, which we cannot list in a one slide or two slides. So there is no necessity to remember the infinite applications that these metals have in their compounds. But we must list out how beryllium is singularly distinguished from others. It forms largely covalent compounds, excepting beryllium fluoride. Beryllium oxide and hydroxide are amphoteric. Beryllium chloride is a Lewis acid, and beryllium fluoride is soluble. Somewhere I must have written. No, I must write down here. BeF2 is soluble. Unlike lithium fluoride was sparingly soluble, is soluble, and other fluorides. Beryllium halides, the Lewis acids, it remains as a dimer. It remains as a dimer and a polymer. Beryllium forms methanides, B2C, others form acetylides, MC2. Beryllium doesn't react with water. Of course, this I have to, with all seriousness, I have to react with water very slow. Because nowadays beryllium has been found to react at an elevated temperature. So I can't write like that. Does react with water. Very slow. You can write down 2 times, very, no harm. Fluoride is an exception. You can't compete. You can't extend the analogy of, small size anion and lattice enthalpy controlling factor. You can't do that. Fluoride is something different, and you have to give a different explanation for that. But carbonate, sulfate, oxalate, chromate, etc., large size anions, these salts of beryllium, they are soluble. So also fluoride. Fluoride being a small size anion, unlike hydroxide, beryllium fluoride is soluble. And of course, the carbonate, sulfate, oxalate, they are soluble, significantly soluble. Beryllium hydroxide is sparingly soluble, and others are fairly soluble because the small size anion concept is applicable here. Now, a chart is there where Soumya says, sir, you missed water in the 5th point. Where is the 5th point? 1, 2, 3, 4, 5. With water, yes. Thank you for reminding, Soumya. Beryllium reacts with water very, very slow. I can't say, as some text will tell you that they don't react. They do. Even some text will say magnesium doesn't react with cold water. You can prepare, you can perform the experiment yourself. Take a magnesium ribbon, put it in water, and use a magnifying glass. See, bubbles will come out. Beryllium, like aluminium, becomes passive with conc nitric acid. Others do not become passive. Beryllium 2+ form complexes. Berylate ion. This is the tetrafluoridoberylate. Tetrafluoridoberylate. Others, they do not form complexes. Beryllium salts are easily hydrolyzed because it is a Lewis acid. It reacts with water. It invites and reacts with water. Beryllium cyanide, this coordination number can go up to 4, maximum 4 in complexes like this tetrafluoridoberylate. It doesn't have a vacant d orbital, so it cannot expand beyond 4. But others can expand beyond 4. It can go up to 6. It can go up to 12. I am talking of the number of water molecules of crystallization. I am not talking about the complex formation. That there is a huge difference between complex formation and this water crystallization. And in transition metal compounds, you will find some of these might be inside the coordination sphere, forming a direct covalent bond with the metal ion. But here, these water molecules are not directly bonded with the metal ions. They are outside with dipole-dipole attraction, so much so that you can separate the crystal. You can't look where is water. It will be white. You can't see water. You can't feel a wet feeling you don't have. It is a crystal. So they are there, but surrounding each positive ion, not the directly bonding. So these fluorido, they are directly bonded with beryllium. So this is a complex. This is not a complex. So, but the coordination number is applicable for complex as well as for the hydrated salts. Here, 6 water molecules can go. Magnesium can go up to 12, not calcium. I'm sorry. So they form hydrated compounds. Others can have their coordination number more than 4, but beryllium is restricted to 4, doesn't have vacant orbital. Now it has got a diagonal relationship with its diagonal element, aluminium. Both of them not readily attacked by acids due to oxide layer formation. They are very passive. They slowly react with acids because they're surrounded by, they're covered by impervious oxide layer. Beryllium oxide and hydroxides are amphoteric like aluminum oxide and hydroxide. They form berylate salts like metaluminate, like aluminate. Beryllium chloride and aluminum chloride both exist as dimers in their liquid state or also in their vapor state up to certain temperature. B2Cl4, Al2Cl6. We shall see this structure in our group 13 program. Both chlorides are soluble in organic solvents and both are Lewis acids because they have a predominant covalent character. Both form complexes. Aluminium can go up to 6. It belongs to the 3rd period. It has 3Ds backend. But beryllium belongs to the 2nd period. It can't. But they form complexes. Both form methanides, B2C, which will produce methane. Aluminum carbide also will produce methane, and the oxidation number of carbon is -4. Thank you for the patient hearing. This is almost 1 hour 20. We started maybe 110. Sorry, 140. We started. This is 240 and 250, 60. 1 hour 20 minutes. So thank you for this patient hearing, some of you, and this is being really prepared for the future generation. Anytime you watch this video, anyone, and if you like it, put a thumbs up. And obviously what I say, often I am really constrained to request for subscription, because I am time and again I am reprimanded by my close nears and dears just to request the audience, the viewers, to subscribe if they have not yet, and if they are following, liking what is going on here in this program. Bye-bye. And next video, we shall be looking into the individual chemistry of magnesium, calcium, and their important compounds. Bye.